Hello everyone, my name is Anwesh Badapanda and in this video I'll be talking about dynamic programming. So let's get started. If you are new to the programming world, you might see the term dynamic programming in multiple places like blogs, videos, editorials and etc. This might sound confusing at first, but as a concept it is not so tough to understand. Let us look at the definition first. Dynamic programming is a technique which can be used to solve an optimization problem by breaking it down into simpler subproblems. It uses the fact that the optimal solution of the problem depends on the optimal solution of its subproblems. It can also be thought about as an optimization over plain recursion. Why? This is because in plain recursion, the solution to a particular subproblem may be calculated multiple times, which increases the compute time. Let us look at this problem visually. Suppose we are trying to calculate the Fibonacci series sums. Let us abbreviate it as Fib problem for the clarity of understanding. And let us fix n as 4. If you're trying to find fib of 4, you first need to find fib of 3 and then fib of 2. To find fib of 3, we need to find fib of 2 and fib of 1 and so on. If we have a closer look, we can see that fib of 2 is calculated 2 times. Fib of 1 is calculated 3 times. Fib of 0 is calculated 2 times again. As I mentioned before, calculating subproblems again and again increases compute time, which causes a delay in the result. Let us look at the difference in the code between two different approaches, that is recursion and dynamic programming. In recursion, we first set a base case. Here the base case is n is less than or equal to 1. If it is less than or equal to 1, we just return n. Else we calculate fib of n minus 1 and fib of n minus 2. In the dynamic programming approach, we initialize an array with n plus 2 terms. We fix the base cases, that is 0 and 1, where f of 0 is equal to 0 and f of 1 is equal to 1. Now we use a for loop to find the terms up ahead. For now, let us take n as 2. So f of 2 will be equal to f of I minus 1. In this case, it will be 1, and f of I minus 2. In this case, it will be just 0, which will be equal to 1 plus 0 equal to 1. F of 2 is equal to 0. F of 2 is equal to 1, sorry. And similarly, for different n, the solution will be different. Now, so far dynamic programming seems like a convenient way to solve problems. But we can't apply this method to all problems. So what problems can be solved using dynamic programming? To be solved by dynamic programming, the problem must meet the following criteria. It must have overlapping subproblems, and it also must have an optimal substructure property. This may sound familiar because we discussed this in the first slide. Since we have already discussed the overlapping subproblems using the recursive tree, let us look at the optimal substructure property. A problem is said to have the optimal substructure property if the optimal solution of the original problem can be obtained using optimal solution of its subproblems. Let us look at the familiar Fibonacci series, where f fib of n is equal to fib of n minus 1 plus fib of n minus 2. Here, fib of n is the original problem, and fib of n minus 1 and fib of n minus 2 are the subproblems. Now let us look at another problem, which is the shortest path problem. Let us say we're trying to find the distance between Delhi and Bengaluru. We can take a midpoint in between, which can be considered as Bhopal in this problem. We can find the distance between Delhi and Bengaluru by just finding the distance between Delhi and Bhopal first, and then finding the distance between Bhopal and Bengaluru, and then combining these to get the solution to the original problem. In this, the sub-problems were the distance between finding the distances between Delhi and Bhopal and Bangalore, and the original problem was finding the distance between Delhi and Bangalore. Now, dynamic programming itself has two different approaches. The first is memoization, which is known as a top-down approach, and the second is tabulation, which is known as the bottom-up approach. In memoization, we solve the bigger problem first by recursively finding the solution to the smaller subproblems. After solving a subproblem, we cache its results. So we don't have to solve that particular subproblem again, and instead we can just look up its value when required. Let us recall the recursive tree for the Fibonacci series problem. After calculating fib of 2 one time, instead of calculating it again, you can just look it up in the cache and have retrieve its value and use it. Now let's look at tabulation. In this approach, we avoid recursion altogether. Instead, we solve all the subproblems first and then fill the results in an n-dimensional table. And using the table, we find the solution to the subproblem, original problem. In this case, the table will be an array. Let us compare the codes for memoization and tabulation. Again, we are using the Fibonacci series problem. In the left side, we have the code snippet for memoization. We set a base case, x is equal to 0, where we just return 1. And we are using the DP array as a cache. Now, in the second condition, we see if dp of x is not equal to minus 1. Then we just return dp of x. Why are we using minus 1? Because we are initializing a dp as an array full of minus 1s. If dp of x is not equal to minus 1, that means we have somewhere already calculated its value and we are just trying to retrieve it now. If it is equal to minus 1, that means we have not calculated its value yet and we calculate the value by using this formula. Now let us look at the tabulation method. Here we again use the dp array and set dp of 0 as 1. We then iterate over the dp array and find the previous values using the we find the values using the previous values. Let's see, for I is equal to 1, so dp of I, where I is equal to 1, will be dp of 0 into 1, which will be equal to, here we have dp of 0 is 1 already, 1 into 1. Similarly, for dp of 2 will be equal to dp of 1 into 2. dp of 1 is equal to 1 into 2. So it's 2. Similarly, dp of 3 is equal to dp of 2 is equal to 2 into 3 is equal to 6, and so on. Now, before I conclude this video, I would just like to show the difference in compute time between simple recursion and dynamic programming. The function fib is a recursive approach. Let's first run this. Now, let's try the dynamic programming approach, that is then Fibonacci. As you can see, the recursive approach was much slower than the dynamic programming approach. I would like to thank all of you for watching my video.